Hello and welcome to this lesson where we're going to look at how you can calculate the speed of water ripples in a practical investigation, which forms part of the AQA Combined Science course for GCSE Physics. So in today's lesson we're going to try and determine the wave speed of a wave, and in this example it's going to be a water wave. So if we are successful and we learn in today's lesson, we understand how to calculate wave speed, look at how you calculate wave speed from experimental values, and explain why different measurements are taken and how this takes place, which falls into the following part of the AQA GCSE Combined Science series 6.6.1.2 Properties of waves. And so in today's lesson we're going to try to calculate the wave speed of a water wave from measurements. Now remember, the wave speed is the speed at which energy is transferred by a wave. It is the distance travelled by each wave every second. So in this investigation we're going to calculate the speed of water ripples through a water surface and then relate this to the depth of the water wave that produces it. So we would need a tray, stopwatch, 30cm ruler and a 100cm ruler. Now we would use a ruler as a depth measure and place 25mm of water into a tray, then place a marker pen underneath the tray as a ramp. Removing the marker pen causes the tray to fall and a wave to be produced. You then measure the time it takes for this wave to move from one side of the tray and then back. Repeat this investigation 3 times and generate an average, and carry out this investigation for depths of 20mm, 15mm, 10mm and 5mm of water. And this will allow you to measure the distance which the wave travels, which will be twice the length of the tray, time how long it takes to go there and back, and use that to calculate your wave speed. So in this investigation, like we said, we would use a ruler to fill the tray to 25mm, but in this case the ruler has a systematic error of 5mm. Now a systematic error is a constant error found on all experimental results. Now you can remove a systematic error by subtracting this value from the results. Now this type of error is due to the measuring device, in this instance the ruler, not reading 0 from where it should do, because it should read 0 and right at the edge of the ruler, but there's this 5mm gap from where the ruler starts and the measuring scale begins. Now this type of error where you're reading a non-zero value when it should be a 0 value is called a zero error. So a zero error is a type of systematic error. Now so you would think about these zero errors on your values and you subtract that systematic error from the measurements that you take. You would also ensure the tray is flat when you're measuring the depth, as it can lead to an anomalous result. Now this error can vary with each measurement as opposed to a systematic error. So we call this type of error a random error because it changes value with each particular measurement that you take. Now a random error can be reduced by repeating the values and taking a mean average. Once you've set up your tray full of water, you will place a marker pen underneath the tray to form a ramp. This is going to act as a control variable. It must be the same for each measurement that you take, so the tray must be at the same angle each time. Now when you remove the pen and produce a wave in the water body, this will produce a wave that travels along the tray, and this will be a transverse wave, a water ripple. Now when the wave hits the side of the container, what will happen is the wave will reflect and go the other way. Now the intensity of the wave will decrease as some of the wave energy is absorbed by the tray, because some of the energy will be absorbed by the surface, some energy will transmit through the surface, and some energy will be reflected back by the surface. Now this means that when a wave hits a surface, absorption, transmission and reflection can all occur. Now when you are measuring the properties of this wave, you're measuring the time it takes to go there and back, so therefore the distance travelled is there and back, so it's twice the length of the tray. Now we can measure the speed of water ripples in this investigation as they're slow enough to measure. Sound waves, light waves, they travel too quickly for us to measure in a school laboratory. Now we can measure the distance that the waves will travel in water with a ruler, and we can measure the time taken by the wave to transfer the energy through water with a stopwatch. We can then use these values to calculate the wave speed by using the equation speed is equal to distance over time. Now the reason why we do the experiment there and back and not just there, so you don't just stop the stopwatch when the wave hits that first surface, is because it increases the distance travelled if we measure there and back, and it also increases the time taken, so it decreases the impact of your error in those measurements, because you'll have error in measuring the distance because you may not hold the ruler completely parallel or hold it from the right position from where the water wave starts, and also you'll have error in when you measure in time by using the stopwatch. Now this means to minimize the impact of their error, the larger the values you take of these measurements, the lower the impact the error has, making your results more accurate. So we call this in science percentage uncertainty. So the larger the measurement, the more accurate the measurement, because the lower the percentage uncertainty, because the error due to the experimenter is a smaller percentage of the overall answer. So the larger the measurement, the smaller the percentage uncertainty. Now in this investigation we'd do different depths of water, so 5 millimeters, 10 millimeters, 15 millimeters and 20 millimeters, and we would calculate the wave speed by measuring the distance there and back and time and how long it takes for the wave to travel there and back, and we'd look at the relationship by filling in our results table. Now remember, you would give all values in each column to the same number of decimal places, which will be determined by the number of decimal places the measuring device reads to. You would then draw a graph of your experimental results, placing average speed on the y-axis and depth on the x-axis. You would then draw a line of best fit. For example, this would be a line of best fit. Now, what have we learned in today's lesson? We know that wave speed is equal to frequency times by wavelength. You should be able to recall and apply this equation to many different contexts, but also you should be able to describe a method to measure the speed of ripples on a water surface in a school lab. So if you've been successful and you've learned in today's lesson, you understand how to calculate wave speed, you can calculate wave speed from experimental values, and you can explain why different measurements are taken and how this takes place. I hope you've enjoyed today's lesson, where we've looked at how you calculate the speed of water ripples via investigative methods, and have a lovely day.